Today, fiber optics plays a major role in today's local area network, and we're going to take a look at its role and its place and all that goes into using fiber optics as well as troubleshooting it in the local area network. Multi-mode is the most commonly used fiber optics standard for local area networks. Here are some of the basics of multi-mode. You can see the light source at this end called the acceptance cone. The light coming in and bouncing throughout the glass tube that makes up the core. On the outside is the cladding, and it helps keep the light inside the small amount of glass that's inside. As we look at multi-mode, the core size of a multi-mode fiber is very large compared to its cousin single mode down here at the bottom. So it allows light to bounce around inside the fiber optics or the glass tube. Notice something else very important. The amplitude of the signal on the input is dramatically reduced on the output. So there's quite a bit of loss in this multi-mode type operation. That makes for the large tube and the use of LEDs makes multi-mode cheaper. But there is such a loss that it can only be used for short distances. On the bottom here, single mode, much smaller fiber optic glass tube. Notice that the input amplitude and the output amplitude are very good, both in and out. So this is going to be the fiber mode that we typically use for long distances. One of the most important things that we can understand is the relative size of fiber optics. Notice this very small protrusion. This is going to be our actual glass fiber. This outside area, which is significantly larger than the glass fiber, is called the cladding. And then there's all kinds of jackets and sleeves that protect both of these. We're going to find that the tube that actually carries the light is incredibly small. The cladding is an important characteristic material that is wrapped around the glass that keeps it from breaking and also keeps the light from escaping. With the emergence of fast Ethernet, we began to really see fiber optics come to the local area network. The 100 base FX standard was 100 megabits fiber optics standard for Ethernet, really brought fiber optics into the local area network. Remember, in the early days, 100 megabits was very, very fast and typically used for backbones between closets and the MDF, say IDF to MDF. So this was one of the first where we really began to use a lot of fiber optics. The transmission distances were basically two. If you were using half duplex, then you could only get about 400 meters, and that was because of collision detection. You could go up to 2 kilometers, about 6,600 feet, if you use full duplex over a multi-mode. When gigabit Ethernet really hit the streets, we can see that many Ethernet standards were created for gigabit Ethernet. We have multi-mode fiber up to 550 meters. We had single mode fiber, 5 kilometers. Keep in mind as we get into some of these Ethernet standards like LX, LX10, ZX, these are typically standards of Ethernet that are going to use single mode, and they predominantly are going to be used by Verizon, Sprint, Bell South to provide such things as Metro Ethernet, long distance fiber runs under the ground. Whereas in the typical local area network, we're going to use LX and SX. Most of us are going to see multi-mode optical fiber in our local area networks. It is cheaper because of the types of light sources they use. They typically use LEDs. The fiber is a little bit cheaper because it's not as precise and small, and it doesn't have the distance that single mode does. We see data rates from 10 megabits to 10 gigabits and up to 600 meters in distance. Here's an example of multi-mode fiber. Notice the jacket is orange. That is typically multi-mode. If this jacket is yellow, that is in most cases single mode. Notice we have some cotton fibers here. Again, we have some jacketing, silicone, polyurethane, whatever. This right here is the cladding. This that you see visibly with your eyes is cladding. Very, very small is a micron piece of glass that goes right down the center. You cannot see it with your naked eye. This is a laser diode. This is typically the type of equipment that is used to produce the light. It is all about the lens and the type of diode that they use, but this is what is used to produce the fiber optics light. Laser light is measured in wavelengths, and so you can see there's all kinds of uses for laser diodes. We're going to slide down here and take a look. Once you get into about the 1064 nanometer wavelength, we're starting to get into fiber optics communications. So you can see as we go higher, we're getting into actually more of the single mode type laser optics. But as about the 1064 and a few below, that is the wavelength that we typically use for local area network laser diodes. You'll notice in the 504 nanometers is where the Blu-ray disc laser diode is used. And some of the other, you can take a look around on Wikipedia and see the other uses for different laser diodes. Here is the LC connector. You can take a look at its shape and size. This is, notice it has two fiber optic runs, one for one direction, one for the other, so we can run full duplex on fiber all the time. In the early standards of fiber optics, they did have a standard for half duplex, but there was no need to do that. And so today, two fiber runs are always required, always full duplex. And so this is a nice, clean connector that brings two fiber pairs to a jack wall plate. This is an MTRJ connector, and this is both, it's got both fibers in here, although you really can't see it as well. You both have two fiber connectors, and it's a very small form factor, just pops into a connector, a jack or a plug, and brings both fiber optics pair to the device or the patch bay. This is your very popular SC connector. Probably the most common usually used connector for equipment and patch bays, SC connector. The ST connector was the early bayonet locking type fiber optic connector, very popular in the early days. It was quickly replaced by SC, but this was, still you see a lot of ST connectors. The actual fiber optics diameter, and including the cladding, for most multimode is 62.5 microns, and the cladding is 125 microns. So this is pretty much the standard for most multi-mode fiber. So that is the diameter sizes for both the fiber optics and the cladding. Here we see single mode, and here we see the fiber optic cable is actually about 8 to 10 microns or micrometers, and the cladding stays a consistent 125. So we drop down significantly from 62 to about 8 to 10 with single mode. So you can see the single mode fiber is very, very small, even compared to its cousin multi-mode fiber. One of the most important pieces of fiber optic cable, as we look at what makes it up, is the cladding. The cladding causes the light to be confined to the core of the fiber, so it keeps the light inside that glass fiber optics. As you bend the fiber optics, the cladding loses its ability to keep the light in the core, and we'll see this as we demonstrate this down. But remember, cladding is designed to wrap around the clear fiber optics glass and keep that light in the center of the core. Here's a good look at some of the more common connectors that we see in our local area network. The ST connector, which was probably one of the originals, quickly replaced by the SC connector. The LC connector was very popular. The MTRJ, which is it's a very small form factor, very popular with equipment where we're going to have high density. The VF45, the FC connector, and some of the others. You can take a look at those. Fiber optic connections are very, very critical. Here you actually begin to see an ST connector coupled with some kind of jack or plug. And you can see that right here, this fiber optic matching has to be really, really precise. So as we mate the two fiber optic cables, remember they're very, very small, 62 microns in size. Everything in a fiber optics connector must be precise. If they're miscoupled, we're going to lose a lot of light, or we're going to diffract light. So when we get into fiber optics, The connectors and the connector systems make a huge impact on the overall stability of your fiber optic system. Here are some great illustrations on some of the issues with fiber optics as we connect, join, plug them together. You can see some of the problems called the end gap problem, where there's a gap between the two fiber optic mating ends, and so we lose light. A mismatch. The angle is incorrect. So you can begin to see all the different problems. Here's you got dirt involved, where you've got a bend. They're not perpendicular. They're actually aligned at an angle. Core mismatches, two different sizes. And all of these things are going to impact light effectively going from one fiber optic cable into the connector and down another cable. So these are the things that cause us serious trouble as we design and build and make our fiber optic network. Here are some of the cable styles. You can see the orange jacket. Remember, if it's yellow, that typically is an indication, not a guarantee, but a good indication that it's probably multi-mode. We see two fibers. Notice the cotton around it. All this is just to protect the fibers. Here we probably have single mode, possibly. Here you can see a whole bundle of fiber optic pairs, depending on, is it going to go underground, is it going to go in the air? All those will depend on the jacket, whether it's going to have stainless steel jacket and those types of things. One of the most interesting things about fiber optics is the relative size. You can see here in this picture where my mouse is, you can see this small, what looks like glass tube. That is not the fiber optics. Over here in this picture gives you a better perspective of what you're really looking at. This coating that you see here is typically acrylic, some type of epoxy material that's around the cladding. Then you have the cladding, which is very, very small, and then inside is this tiny 6.2, 62.5 micrometers or micron glass fiber tube. When you look at this, you're actually looking at this coating. That's what you are seeing. Your eye cannot see that core. You will have a hard time even seeing the cladding. So when you look at the relativeness size of this, you're thinking this is the glass. No, you're not even close to the glass. Way down here, very, very small, beyond your ability to see with your naked eye, you can't hardly see the cladding, yet alone the core. What you see mostly is the coating, the epoxy, acrylic, whatever is the particular coating for that particular manufacturer. You typically have to have a 200 power microscope in order to see this tiny dot. 200 times. This is an example of multi-mode and single mode, and you can see the relative differences in their size. Remember, multi-mode is typically what we're going to use in the local area network. Verizon, Sprint, Bell South are going to be single mode, long distance runs. When light is shot down the fiber optic tube, some of the light is lost in the cladding. Some of it, so you can see this is a nice illustration of how much of that light is actually maintained inside the fiber optics tube versus how much is lost in the cladding material. We want to keep as much as possible in the fiber optics tube. If it goes in the cladding, it's considered loss. We want the internal reflection to be very high. We want the light beam to stay within the glass. If it goes into the cladding, we're going to lose light and we'll have an amplitude loss from the input to the output. Another property of fiber optics is that the light that is injected into the fiber optic tube has to be within a certain angle, and you can see that it's called the numerical aperture. So you can take a look at, they're giving you a nice, otherwise if the light is sent in, it will be absorbed by the cladding. Here you can see the effects of attenuation and dispersion. So take a look.